So thank you very much. Unfortunately, by the way, I was not affected by the Adobe patches because Adobe Reader was not part of Pwning this year, but I'll come to that in a second. So welcome to my talk. This one is going to be about Pwning Adobe Reader by using the embedded XFA engine. So let's see what's on the menu for today. I'll start off with a short who am I and explain afterwards a little bit what my motivation behind this talk was. Then I'll do a short introduction to XFA. I really will keep this short because we have quite some content to cover. Then afterwards we'll dive into XFA internal stuff, like having a view on the objects in the XFA engine, and most importantly the JF Cache Manager. And then we'll have a look at how we can use the knowledge of the objects and the Cache Manager to finally exploit the reader in a very reliable way. And afterwards, of course, we'll have a conclusion and Q&A. So short about me, I'm Sebastian. I co-founded a small IT security consultancy in Germany in 2009. We're mainly focusing on pen tests and code audits, stuff like that. But we're trying to do as much research as somehow possible, because that's the fun part. I mean, auditing PHP web applications is also nice, but digging deep into Windows kernel or Adobe Reader or whatever, that is much more fun, and that's what we love to do. So I would describe myself as a low-level addict. I just love reverse engineering, bug hunting, exploitation, all that kind of stuff. So in the past, I found quite some vulnerabilities, took part in Pwning in 2014, and yeah, that's all about me. So about the motivation behind this talk. We did a fuzzy run at Siberas in 2015 with the goal actually to take part in Pwning in 2016 again. Unfortunately, as you might have noticed, it was not part of the targets this year, so that was a bummer for us. We did XFA fuzzing not on like Google scale. We only had 128 cores available, but it still yielded thousands of crashes. So we really had a lot to analyze. Around 20 bugs are right now identified as unique. And the problem with all those crashes was that the analysis of the crashes was quite a pain. And I will show you with a typical reader crash why this is so difficult to analyze. So this looks awesome. We get a crash, an access violation. EAX points to somewhere, but not to mapped memory. But if we have a look at the function where we crash, it's DLL unregister server with some huge offset, that doesn't look too promising. And if we have a look backwards a little bit and see where the bad reference comes from, then we see, okay, it comes from ECX. And usually what you do as a bug hunter, you do a bang heap on it to see where the allocation comes from and what size the object has. And if we do that, we see, all right, the user size is CCD8. That must be some kind of very huge object. Of course, it's not. It's a huge chunk in which we land. And if we just subtract the value ECX from the base address of this huge chunk, we see that we land somewhere in the middle of it. So page heap for that is rather useless, obviously. And if you also do a stack trace, we see basically nothing. We always get those DLL unregistered server functions, not too helpful either. So yeah, Adobe Reader obviously has no symbols, and they don't even offer RTTI infos, so you're kind of left with no function names, no object names, vtable information is not there. You can forget about the stack traces, page heap is useless, not too good for us. So all of this makes root cause analysis of vulnerabilities very hard. And if you do a large fuzzing run, then it is also very difficult to do crash triaging. So like finding out whether a vulnerability is unique or whether it's exploitable, or find out infos about the objects which are involved in the crash. That is all very hard to do. So the question for me was, how do we actually analyze those crashes? And finally, how do we exploit those crashes? Well, it's pretty obvious that we need context in some way, and we need to recover symbols if that is possible. So let's have a short look in the past. There was a little bit of XFA research when in 2013 this XFA exploit surfaced, and some researchers did analyze the vulnerability behind it, but it was mostly focused just on the vulnerability and the exploit itself, but they did not choose a generic approach to dig deeper into it. So really in-depth research is still kind of missing. So what I wanted to do was write tools to recover some of the contextual information, and of course lower the bar for other researchers, guys like you. If you want to do Adobe Reader research, the tools that we're going to publish on our GitHub in the next days, they might be pretty useful for you. Of course, with these tools, I wanted to facilitate vulnerability discovery, the root cause analysis process, and also crash trial during fuzz runs if you want to do that. And of course, one important point behind my talk is giving some background on XFA-specific exploitation. All right, a brief introduction to XFA. XFA is the XML forms architecture. So whenever you open a form that you have to fill out in a PDF, then probably XFA has something to do with it. The technology behind it has been invented and implemented by JetForm, which was later Excelio and acquired by Adobe in 2002. This is not a standard, it's a specification which is long. It's nearly 1,600 pages long. That already tells you, yep, there's quite some attack surface behind that. And what XFA actually does, it brings the dynamic behavior to the otherwise rather static PDF world. So you get forms that can dynamically change their layout. And the dynamic part of the XFA stuff, this is driven by SpiderMonkey. And the latest version, Adobe Acrobat Reader DC, it's called now Acrobat Reader, not anymore Adobe Reader. It's driven by SpiderMonkey 24. XFA itself is not supported by many PDF readers yet. Most notably, of course, Adobe Reader or Acrobat Reader, Acrobat, and Foxit Reader supports it. But many other popular readers do not support it, like Chrome, Chromium. Firefox does not support it, or the Windows PDF Reader as well. So that's why I also think if that doesn't change, Adobe Reader is here to stay for quite some time, probably. So the XFA form data itself is an XML structure which is embedded in the PDF in a so-called XDP packet. And within this XDP packet you find JavaScript, and this JavaScript is always executed upon certain events, like the document is fully loaded, or a user clicks a button or something like that. Let's have a look at a practical example. And I hope this is kind of readable. So the XML blob that you see here, it always starts off with the XDP root tag. And below that you always find the config DOM. The config DOM contains elements which are important for XFA processing. And you have another DOM which is actually the most important one. It's called the template DOM. And the template DOM contains all the important objects that you as a user will later see in the PDF, like buttons, text fields, stuff like that. And looking a bit further down, you also see the event object, and those event objects are those which contain the actual JavaScript code. Like in this case, you see it's just an app alert 1337. But that's just to give you a basic idea how this XDP packet embedded in the PDF looks like. I could spend probably hours now to explain all the different DOMs which exist in the XFA engine, but I will just say there are many different ones. There are many, many objects, in total like over 200 of them, and they all can be accessed over JavaScript and used in the fuzzing process. So as you might be able to imagine, this is a really, really huge attack surface, and probably we'll see many more vulnerabilities in the future in there. So let's switch on to the XFA internals. It actually all started off with a tweet by Niels, who wrote Frigo over Twitter. I found a Solaris build for Reader, which seems to contain symbols. And there's a strange allocator in that, which is called the JF Cache Manager. When I saw it, I was like, oh, okay, this is pretty nice. So maybe there's a way to recover the symbolic information and use it in newer versions. So the first step what I was doing was, of course, to search for the newest version to get the most recent symbols out of it. And what I found is, was that the Solaris version 9.4.1 was the newest one that I could spot. So what we need now, when we have the symbols for an old or a rather old Solaris version, we need a kind of reliable heuristic to port the symbols from the acroform.api, which is the module which implements the XFA functionality, to port these symbols to the acroform.api DLL of newer Adobe Reader or Acrobat Reader versions. But I stumbled over quite some problems. One was that the code for the 9.x versions is rather old, from 2012. And there have been quite some code changes in it. So if you have a look at the Solaris version, you see it has 48,000 functions, which is still a lot. But if you have a look at Acrobat Reader DC, it has 95,000 functions, so the function count nearly doubled. And the problem with diffing the two modules, the old Solaris version and the newer acroform.api from a recent Windows version, was that the compiler for the Solaris binary really did some heavy inlining with functions, and so matching it up with Diaphora, for example, was a total fail that didn't really work, mainly because it turned up too many false positives, and that is something that you do not want to have at all, because it will totally confuse you if you try to reverse the binary, find out some basic functionality in it, and if you're faced with wrong function names, that is definitely problematic. By the way, nothing against Diaphora. This is a really, really cool tool. It was just in this case not really usable. And another problem was that structures, objects, and the vtable sizes differ slightly as well. They don't differ much, but it's enough to totally screw up your heuristics, so you can't really use that. So I had to try a different approach. My approach was to trying to understand Reader in a certain way, which would help me to find a very bulletproof way on how to recover symbols. And I focused not on quantity, trying to match like 20,000 functions, but I wanted to focus on the really important ones. So I wanted to have the symbols ready for every version for the heap management. And I wanted to have the most important symbols concerning the objects. So let's talk about objects. What is useful to know about those objects? First of all, if you have a crash, you want to identify it in memory. You want to know, okay, we have a crash, these objects are involved. What kind of objects are these? So you need to identify them somehow in memory. What would also be nice to have are the vtable offsets in the binary for the different objects. Also nice would be to have all the methods and properties which are exposed to JavaScript, because then you wouldn't have to read the 1,600 pages. And something that would also be very interesting to have are the entry points in the binary for all the methods and property getters and setters which are exposed to the JavaScript engine. And as a bonus, it would be nice to have all the function names of the vtable entries. So if you have, for example, for an object, call vtable offset hex 80, that you know exactly, okay, this is get screen offset or something like that. So let's see what we can recover from that. My first attempt when I was reversing the old Solaris version was a function which is called getClassTag. And what it does is simply it returns a class tag ID which is stored at offset 10 in the XFA object. And I thought, hey, this is pretty nice because that might match up with the newer versions. So if we have a look at the Solaris version, at the constructor method of the field object, we see that it writes the static value hex 86 at offset 10. So that is our class tag. And now if we have a look at the field object in memory under Acrobat Reader DC, we see that it has the ID 8E. So that doesn't match up, and I also tried it for other objects. It is not the case that it's only shifted by 8, but it just doesn't match up. Those constants are obviously not constants, so there was a fail. I couldn't use this class tag. But I had a second try, and I found this type method. And the type method is located always at vtable offset 8, and for every XFA object that you have in Reader. And it just returns a static value. For the field object, it just returns the static value 7C46. And if you have a look at this function for the field object in Acrobat Reader DC, you see, okay, this ID looks much better. It seems to be static. And it really is static, so that can be used to kind of identify the objects in memory. So how do we go about that? We have the old Solaris version. You get a match between object name and the corresponding ID. And as you have the ID, you can just search through the newer versions of acroform.api and search for binary patterns, because the instructions in the type methods are always the same. It's always move static value to EAX, return. So you can identify all the type methods for all the objects just by searching for a simple binary pattern. B8 is for move EAX, then you have the static value as an integer value, and C3 for the return instruction. So searching through that gives you all the type methods, and having all the type methods to all the objects, you can just go to the beginning of the method, search for the xrefs. You only have one xref to all these type methods, and you find immediately the vtables. So that is pretty nice. We can safely, really 100% safely for all the versions, identify all the XFA objects which are part of the engine. So we can have a check on the first item on our list. We can now identify the objects in memory, and we get the vtable offsets. So that's already pretty nice. So let's have a look at methods and properties and what we can find out about them. So at vtable offset hex 34 into the vtables of each XFA object, we have this function getScriptTable. And this function is also pretty short, and it contains one reference into the data section of acroform.api, and it contains the so-called MoScriptTable structure. And this structure contains all the relevant information that you want to have about objects, about their methods and properties. So let's have a look at how that looks like. So it starts off with the, in our example again, with the field object, with the MoScriptTable structure. And this MoScriptTable structure starts off with a D-word, which is again a pointer to another MoScriptTable, one level above in the object hierarchy. So the first entry is a XFA container implementation MoScriptTable, pointing to a node implementation MoScriptTable. Then you get the tree, and you get the object, and it always ends with the 0. So from parsing just the first D-word in line, you already get the object hierarchy, which is pretty nice. So the second field also contains the object name. So you have the field, and you have the parent class, which is container, parent class is node, tree, and finally you have object. And the third and fourth entry into those most script tables are pointers to tables. And those tables end with a 0 and just contain pointers again to property structs in this example. And the property struct is also very simple. In the first field, it contains a pointer to the string of the property, in this case raw value. And just below you find the setter and the getter function, which is nice because now you have the property to a certain object and you know exactly where the setter and the getter method can be found in the binary. The setter method can, of course, be 0. In this case, it is a read-only property. And you also have a method table. So this method table is just like the property table, a table of pointers, which ends on 0 again. And the method structure is even more simple. It contains a pointer to the method name and the function pointer to the actual function in the binary just below. So with that simple structure, it's very easy to parse. You get all the methods and properties and getter and setter entry points in the binary, which is really nice if you want to have some orientation when you get a crash. Where is my function call and which parameters are passed to the function, stuff like that. So we can also check the third and the fourth item on our list. So what is remaining is actually only getting the function names of the vtable entries, and that I have to say is still to do because it is far from trivial. You have the problem that for different objects, certain methods are virtual methods are added or replaced, and there is no generic approach somehow to find that out. But maybe I will find out a nice method, but still this is to do. All right, let's switch over from the objects to the cache manager, which is the custom allocator, which you can find in the XFA engine. It's a very simple heap manager, LIFO style, which stores, as we saw in the first screenshot, its data in rather large chunks. And in those chunks, you find the smaller data blocks. So you might also know this from gmalloc, for example, or other specialized heap allocators. And like the other specialized heap allocators, this is mostly introduced due to performance reasons. And the fun thing about it is it doesn't really have any security features. So things like heap isolation that you find in the newer Flash versions or in Internet Explorer, this is not present, or anti-UIF mechanisms like memprotect, the older one, or the new memgc, you don't find anything of that. So you already get a sense of this has not been designed with security in mind. Sure, a short disclaimer for the next slides. I can't dive too deeply into the allocator because this is not really possible in 45 minutes. But I will only show you the relevant parts that we need later for the exploitation part. So I'll try to explain only the relevant stuff. I will release in the next few days a paper as well, which will cover it a little bit more in depth if you're interested. So let's have a very simplified version of the JF Cache Manager. You always have allocator structures. The main or the basic structure is the JF Cache Manager. You have JF Memory Cache lists and you have the JF Memory Cache. I'll explain it in a second. But those allocator structures, they manage those big chunks that actually store data, and they always have one chunk for a certain size. And in this chunk, you have afterwards all the smaller blocks, your actual data buffers. And the JF Cache Manager, for a different size Y, manages another chunk of another size with, again, those small blocks stored inside the big chunk. So let's have a look a little bit more in detail into it. I will cover now the allocations of size smaller than 100. The allocator handles allocations of size greater than 100, hex 100, a little bit differently, but having a look at the sizes under 100 is really enough to understand how the whole thing works. So at the root, you always have this JF Cache manager structure. It has size 434 hex. And it starts off with a V table, and at offset 8 it has this pointer to structures for the sizes which are larger than hex 100. But at offset hex 18 it starts off with an array of size hex 100, hex 400, sorry, to store pointers for each size from 1 to hex FF, which are required to manage the chunks. So each pointer in there points to a JF memory cache list. And the name list already implies that it points to some kind of array. And these arrays contain, again, pointers to JF memory cache structures. And that's actually the point where it gets more important. That's why I colored them in red. The JF memory caches are structures which each of them manages one chunk, and they are actually those structures which are decisive for the allocation and free handling and everything like that. So those JF memory cache structures, they point to the blocks of the different sizes. So that's in brief the whole structure of the allocator structures which are involved. So wrong direction. So talking about the size of the chunks, they have the size of the chunk is derived from a certain formula. You see it here. So for example, if you have an allocation size of hex 64, just put it into this formula, and you will see, for example, for size hex 64, you will find the chunk size of CB20. So it would be kind of logical to say, okay, I have a crash and I find my object lying around in this huge chunk of size CB20. It must be of size hex 64, right? Wrong. This is unfortunately not the case, because JF memory cache lists, they can manage blocks of multiple sizes. So what that means is that blocks of size X and of a different size Y, they can both end up in chunk Z. So an allocation of size X will be placed in the same chunk as the allocation of a size Y if the allocation of size Y larger than X has occurred before, and if the size X is in the same range as size Y. And those ranges are always defined by powers of 2. So you have a range, for example, from hex 20 to hex 3F, hex 40 to hex 7F, hex 80 to hex FF, and so on and so on. So in short, what the algorithm basically does is checks if the block which is about to be allocated, does it fit in a chunk that we already have? And if there's a chunk already available, it just takes that one and fits the block into this chunk which is already present. So words are always a little bit hard. Let's have a look at it in graphics. So you see it on here, the size hex 64. We already allocated an object X and a string of length Z. So we have two buffers of size hex 64, which are placed in one chunk, of course. And now we have an allocation of size hex 48. And since this is in the same range as size hex 64, the allocator will decide to just place the object into this chunk. So let's take a look at the structures within the chunks. On the left you can see the JF memory cache, so the main structure for the allocations, and it always starts off with the block size. And in the example over here you see that the block size is always hex 10. You have a max entry in your structure, which kind of gives you the maximum amount of allocations that one of the chunks can hold. And of course, you have a chunk pointer, pointer to this chunk here, and an allocation count. And we have the initial state here, so no block in here has been allocated yet. So the allocate count is of course 0. And very important is the next alloc pointer, which is stored at offset hex 20 into the structure. And this one points to a list head. And this is the beginning of a linked list. You always have those flinks, the forward links, linking together a single linked list of the free blocks which are available in the chunk. So let's have a look at when we allocate our first block in this chunk, how it looks afterwards. So after the first allocation, the next alloc pointer is overwritten with the flink. So it basically just moves one position further down. And the flink is overwritten with a pointer back to the JF memory cache. You see it up here. And of course, the allocs pointer is increased to 1. The next allocation does the exact same. Moves the next alloc pointer to the next flink. Here we override the flink again with a pointer to the JF memory cache structure, and the alloc count is increased to 2. Same with the third allocation. So this is just to give you an idea how it works. It's actually a pretty simple algorithm. So if we free now the second block in here, as you can imagine, the next alloc pointer is going to jump up here, because this block is being freed, and the next alloc pointer just becomes the pointer to be freed -4, so that we have a new list head in here. And the JF memory cache pointer is overwritten with a flink again to complete the single linked list. So this is actually a very simple and also very fast algorithm to allocate and free the blocks within those chunks. So if you still don't like the JF Cache Manager, which I kind of understand maybe, and you're still missing page heap, you can just use one of the scripts that I'm going to put up on our GitHub and get an offset from it, which is called JF Cache Manager Active. And this is actually just a Boolean value, which is set to 1, and it indicates that the JF Cache Manager is active for the XFA engine. Basically, you only have to switch it from 1 to 0, and then you have switched off the JF Cache Manager. Of course, you have to save the binary and replace the binary, and if you start Acrobat Reader afterwards again, you have basically switched off the JF Cache Manager, and you can use page heap again. This is very nice, and also a very nice thing if you do fuzzing. It kind of makes sense to switch it off. It also facilitates crash triaging. So let's have a look at how we can exploit that thing. In my opinion, always 3 factors are important to exploitation. First, we need to understand what kind of vulnerability you have. And in order to understand the bug, you need quite some background information. And the information that I gave you in this talk, and which will be available through my tools that I'm going to publish, this is going to make it easier. So we kind of have a check there. The second part of it is always you need to handle the heap and understand the heap and leverage it in a way that you need it to. So we've handled quite some parts of the JF Cache Manager. I guess we can make a check there as well. But there's a third very important part, always when it comes to memory corruption, and that's what I'm talking about here. You need to know your corruption targets. And so we have some goals when we want to do exploitation here. First of all, we want to bypass ASLR. Of course, Acrobat Reader is a full ASLR target, so we have to get around that. we need to corrupt certain bytes to cause a memory leak. As soon as you know one of the module base addresses, then you can craft your ROP and go on with your exploitation process. But first of all, you need your leak. What we would like to have is a flexible override target. So not something that you can only exploit if you have the kind of perfect vulnerability where you have a write what where vulnerability. This is of course very easy, but I wanted to have a really flexible override target, like if you have an INC or a 0 byte or dword write or a static override of some address that we could use for that as well. And I wanted to find a technique which is fast, reliable, and most importantly, independent from OS and the reader version that we have. Because something that you do not want to have in your exploit is like, if version is Adobe Reader 10, then do this, and else do something else, because just your exploit just gets bloated, and it's most of the time not good for its reliability. So the idea that I came up with was to attack the metadata contained within the chunks. And so we have two possibilities. This is the example again with the block size of 10. You can attack the flink. This is in the case that the block is still free, and the exploitation mechanism is triggered when the block is being allocated. Or you can hit the JF memory cache pointer. This is the case when the block is obviously allocated, and the exploitation mechanism triggers when the block is freed. So I can tell you that both methods can be abused to create a very reliable memory leak, but I will explain today the technique with the flink, because it's just super easy. You will see that. So back to the initial situation. We'll just do a hypothetical approach first, and then we'll do a more practical approach afterwards, where we really step through the various steps that you have to go through if you want to exploit that. So yeah, the initial situation, as I said, is again, no block is allocated, and you have the single linked list of flinks. And let's take the first flink as our override target. And what you need to be able to do, you need to somehow override the flink so that it points afterwards to attacker controlled data, which is not hard to do. Just corrupt the pointer in some way so that it afterwards points to your data. That is easily doable. Acrobat Reader is still an x86 target, so with a little bit of heap spray, that is easy to do. This is still very flexible, as I said, so you can do this with kind of any kind of memory corruption. So let's see what happens now that we've overwritten the bad flink and redirected it to our controlled data if we allocate the bad block. So the next alloc pointer is overwritten with the bad flink. You see that it points now down to attacker controlled data. And the flink is again overwritten with the pointer back to JF memory cache. Now what happens when we allocate an object of size hex 10? The next allocation will return the data buffer after the flink. And now we're in controlled data area, so where our object will end up is in the middle of controlled data. So what you basically get is a vtable in the middle of your controlled data region, which is of course nice to have. As soon as the vtable is in a controlled area, maybe you sprayed it with strings, maybe you sprayed it with float arrays, just as you want to do it, then you can just simply read out the vtable. And it's of course trivial afterwards also to control this, because either you just free the string and override the offset where your vtable is with data you control, or you directly override it with the float value. After the specification here, IEEE 754, you can directly control it, and as soon as you do something with the object, some vtable method is going to be called, and that is basically game over. So let's have a look at a practical exploitation example. And we need some kind of setting. So what I will describe is the setting of a 0D write primitive to an arbitrary address. So the plan is to attack a flink in a chunk of block size hex 180. And so the corresponding target size will be hex C68C. So some of you might wonder, why does he choose the size hex 180? And that has a special reason. Hex 180 is the size of the JF document implementation object, and that is the first object that is being created on the JF cache within this range, size range. So, as you remember, this the range mechanism implies that every object or every string afterwards which is allocated in the range between hex 100 and hex 180 will be placed in the same chunk. And the biggest object that we can create dynamically from XFA is the template object, which has the size hex 140. And yet, due to the range mechanism, this is going to end up in the same chunk. And this is something good to use because it's by far the largest object that you can create dynamically from your JavaScript. And the big advantage is that within this chunk, it's rather quiet because not many allocations happen there. And that's basically something that you want to have during your exploitation process, some area of memory where it's rather quiet. So first thing that we do is just spray strings or arrays, just as you want to do it, of the size C68C. And it's enough to spray around 5,000 of them, so you get a spray of around 250 megabytes. What you want to have is that the address, this is arbitrarily chosen, but this works very, very stable. The address hex 10101000. This one will be mapped, and this will be our target address for the first shot. So we do our 0D word override to this address, and we will hit some buffer, and we call this buffer X. So after we did the override, we just search through our arrays or our strings, and we find that at offset so-and-so we have corrupted data. And what you can immediately compute from that is the starting address of your... Whoops. Doesn't work anymore. Ah, there it is. Of your buffer X. So you, with this override here, you can directly compute the starting address of your buffer X. So you get a kind of orientation where you are in your virtual memory. So the next step is we want to free our buffer X, throw it away, and replace it with a chunk. For that to happen, we need to allocate a certain amount of objects or strings which will be placed in our target chunk. So it has to be of size between hex 100 and hex 180. As I already said, we can, for example, use the template objects for that. And something which is also required, we need to have the flink here at the end still. So this block here at the end has to be free, because if we just allocate an arbitrary amount of objects, template objects, for example, this one here will not be free, and we will not be able to leverage the flink override technique. So how many of them do we have to allocate actually? First of all, before freeing the buffer of C68C size, we should defragment, of course, the JF cache of this size. Even though not many allocations happen there, we should do this to ensure that no more holes are left in the JF cache heap. And after freeing the C68C size buffer, we have to allocate exactly 132 template objects. And the reason behind it is actually pretty simple, because hex 184, which is our chunk block size, plus 4, because due to the flink, times 132 is the size C810, and this is just above our block size. So one chunk has to be allocated. And we can be actually 100% sure that the last flink in our buffer is free. And that gives us exactly the situation that we want to have. That this flink here is still available. And it is pretty simple to compute the address of that, because we know the starting address of the block, and 130 times the block size plus 4 just gives you the address of the flink over here. So now we can do our partial override, so that the flink points to 10000, and this is again in a controlled area. So now we can allocate our template objects of size 140, and what we get is the template object will exactly be placed into our data, and we have the situation that I explained before. You can just search through your strings or your arrays or whatever you have and find the vtable, and that's all about it. ASLR is bypassed, Acrobat Reader is pwned. And as I said, EIP and ROP is not something that I will dive deeply into it, because it's obvious that it's very, very simple to do. So we have a short conclusion. This is a very easy and a highly effective technique to leak data. It's very simple to do. And you don't even need a global read-write primitive, as you had, for example, a few years ago, or years ago, in Flash, when you override the length field of a vector or something like that, which gives you basically access to the whole virtual memory. This is, of course, nice to have. I didn't find that in Reader, but obviously we don't need that. This technique works pretty well. This is completely version independent. I tested it for version 9, 10, 11, and DC, and it works for all of them. And it's completely OS independent. If you do it on XP, if you do it on Windows 10, it will just work the same way. And it's very fast. If you do the string technique from your initial if you have the situation with the 0D word override, which triggers very fast, then you have basically from start of your exploit until you get code control in under a second. It happens very, very fast. And as I said, it's a very flexible technique that you can use with almost every kind of override. So what we have here is a custom allocator, which is perfect for us if we want to play around with the reader, because it's a perfect target for memory corruption scenarios. Thank you for your attention.
Thank you, Sebastian. Very good. Questions? Okay, we can do 2 questions, all right?
Hi, thank you. I wanted to clarify something. When you said that you allocate, all the stuff that you allocate are actually in the JavaScript code inside of the XML element? Like, how do you act, like all of these allocations are somehow created by the input PDF file? How does this happen?
Greater is the PDF file.
Like, how do you actually allocate all of these things? Like, what is the input that you give to the?
Well, it's just one JavaScript method, which is called xfa.template.createNode, and afterwards you give that the string of the object, in this case the template object. So if you do create node template, then you will allocate one of those objects. And if you want to allocate this chunk that I've been talking about, you just have to allocate 132 of them.
And how do you control like when they get deallocated?
Well, they are allocated if you call create node. For you to know, I will also publish on our GitHub account a sample exploit that works together with the PyKD plugin, which emulates a 0D word write, so you can have a look at it, how it works in detail. I couldn't go into detail how the JavaScript and the allocation routines and everything works. But if you have a look at the exploit that I will publish, then you will see, okay, that's the way it works. Of course, I left out some details because 45 minutes is very short to cover real deep technical content. But if you have a look at the exploit and also at the paper that I'm going to release, it's going to be explained in more detail there.
Thank you.
Sure.
Last question. No? All right. Thank you, Sebastian. Thank you very much.